Okay. Hello everyone. My name is Izzuddin Al Azziz, and here I'm back to tell you about the integration of equations in the numerical methods. Okay. Equations. We know that functions to be integrated numerically will typically be of the forms, table of values, or a function. The form of the data has an important influence on the approaches that can be used to evaluate the integral. For tabulated information, you are limited by the number of points that are given. In contrast, if the function is a variable, you can generate as many values of function as are required to attain accuracy. So there are two techniques that are expressly designed to analyze cases where function is given, and both capitalize on the ability to generate function values to develop efficient schemes for numerical integrations. And the first method is based on Richardson extrapolation, which is a method for combining two numerical integral estimates to obtain a third, more accurate value. The computational algorithm algorithm for implementing this is in a highly efficient manner is called Romberg integration. And this technique is recursive and can be used to generate an integral estimate within the specified error tolerance. And the second method is Gauss quadrature, and the values of function for the Newton-Cotes formula were determined by the specified values of x. So for example, if we use the trapezoidal rule to determine an integral, we were constrained to take the weighted average of fx at the ends of interval. Gauss quadrature formula employ x values that are positioned between a and b in such a manner that a much more accurate integral estimate result. So we go to the Romberg integration first. So what is Romberg integration? So Romberg integration is one of technique that is designed to attain efficient numerical integrals of function, and it is based on successive application of the trapezoidal rule, or I would say in a simple way is to improve integration in accuracy by using Richardson extrapolation. And Richardson extrapolation is want to make an estimate of previous two integrals into one new integrals with less error and higher accurate. So in this Romberg integration, we using trapezoidal rule. And what is trapezoidal rule? It is an approximation of a function with the shape of trapezium. So this formula here, it is basically an area of trapezium. B minus A is a height, and FA plus FB is the size of trapeziums, the parallel sides. Okay. So if we want to make more accurate, we can add the segment. We can add the segment in the curve like this. This is the segment 1 and this is the segment 2. And if we have two segments in one curve, we're using this formula right here. This is Romberg integration, and this edge is this, and also right here. And uh, this formula is basically a generalization of sum to integrals into one. So in Romberg integration, basically the number of edges Hn is always be half of Hn minus 1. So you can take example, let's say it is the I1 integration 1 and H1. So this is the H2, and basically we can call it like H2 uh, half of it, half of the H1. Okay, and this is a general formula. The H1 is uh, this this is literally true value, and this is the value of approximation, uh, and add to and sum it with the value of error approximation. And because we integrate a curve with a curve that I've that is literally same with the same interval, so we can take formula like this. This is the simple formula. So basically each one is literally same. And we go to the next slide. So this is a error approximation for the Bloomberg integration, and this one is literally in constant, and this one we also in constant, so it could be say the error approximation is equal to k h quadrat, and we can take the ratio like this. In the first, we have also k because it's also in the same value, so we can erase it. And then this EH2, we move that into this segment, so we have the value of this, and the formula of this we substitution into this formula, in the basic formula, and then we have this, and also uh, we have also this formula after we simplified it. Then we go to the next Next slide. So we have this formula, and then so before that we have a EH1. So the value of EH to this, we substitution in this formula, then we have this, then after that this is the result of Romberg integration. And this is the form of the basic form of Romberg integration, EJK, as you can see right here, and I can show you like this is the H1, H2, I3, and what is IGK, and what is that? I will tell you in here. So the K is actually step, so like K1, K2, K3, it is the same as step 1, step 2, step 3, and I1 is dari G1, G2, and G3. So like I said before, the Romberg integration is we take two integrals right here, and then we make it into the new integral with higher accuracy, and then we could also take it into the step 3 to having more accurate and less error. Alright, I think we could see in the example. So okay, I'd like to continue. Okay, so this is an example for Romberg integration. This is the basic formula we have in here, and this is the example, the integral of 0 until 2 with the exponential sin x divided by 1 plus x squared. So I want to have the error, the percentage of error to be lesser than 1%. So how we get it? Actually, we can use the more segment or steps, and I'm using steps right here. And this is the value of the function of this, and also like the way around you can see as well. And what is 2 is 2, this 2 is actually the edge of the integration for this, and like I said before, in this framework integration, Hn is always be equal to the half of Hn minus 1. So this, the first segment is 2, and the segment number 2 is going to be 1, and the segment of number 3 is going to be 0.5, and the segment number 4 is going to be 0.25, and this is the iteration 1, 2, 3, and 4. This is the step. We have the first step 1, 2, 3, and 4. And in the first step, using the trapezoidal rule with this formula, as you can see. And when we using the Rumber integration, use it in the step 2, 3, and 4. Why? Because using this to create the new integration will have with lesser error and higher accuracy. And this in the step 2, we get this, and step 3 we got this, and the step 4 we only have one integration. This is the value, and this is the case of error of this integration. We have to find the error is actually the absolute number of the k6 minus k6, and then divided by this, the k6, and it's also the same for the others. And at the end we sorry, so at the end we having the least number of error. It is actually the 0.0026%, the percentage of the rubric integration. And I think that's all from me. Okay, wassalamualaikum warahmatullahi wabarakatuh.